Hello everyone, I'm Sihang Liu. Today I'm going to talk about my work, cross-failure bug detection in persistent memory programs. This work is in collaboration among University of Virginia, University of Michigan, Penn State, and VMware Research. And this work was originally published at ASPLUS 2020, and now I'm presenting at this year's PIRL. Before I go deep into details, I'd like to have a brief summary about this work. We already know that programming for persistent memory is hard and error-prone. This is the reason why we have so much programming support from hardware transactions to software transactions or optimized file system for persistent memory to help us make persistent memory program much easier and correct. We identified that previous work has been focusing on the correctness stage before failure by providing detection tools, for example. However, in this work, we found that crouch consistency actually relies on the stage both before and after failure. And there's an interaction across the two stages. For example, the post-failure stage, the stage after failure, may need to read from some log to perform the rollback, or read from a checkpoint to overwrite the existing incomplete updates. And those interactions, if they are incorrect, then the recovery is not done properly. So in this work, we define the cross-failure interactions between the two stages, and we further provide a testing tool called cross-failure detector that holistically tests both stages of cross-failure to make sure the programs are correct end-to-end. First, I'd like to talk about the background about persistent memory. Persistent memory features high performance, byte-addressability, and data persistence. An example is Intel's recent released DC persistent memory module, which has been widely available these days. For example, the server on my back is running persistent memory. Persistent memory has the feature from both the conventional DRAM and the conventional storage technology, which is high performance by addressability and the persistence and high capacity. Persistent memory features better performance, not just because it is a faster device than the conventional storage due to the more advanced Optane technology, but also because persistent memory allows the program to bypass operating system interactions by directly accessing the data stored on persistent memory. For example, using the DEX support. Because of the absence of the file system, persistent memory needs to ensure the crouch consistency of the persistent data, which I'll talk about later. The program in this way can recover to a consistent state even if there's a failure. And in summary, the direct access to persistent memory benefits the performance but makes the programming for this device much harder. Now let's move on to the system integration of persistent memory. Conventionally, the software accesses the file system for the persistent data stored on the disk, for example, and the file system maintains the crouch consistency mechanism to guarantee the program can recover in case of failure. Okay, now we have persistent memory. Then it seems like file system is unnecessary because the persistent memory provides the opportunity of direct access data, right? But the downside is the program itself needs to guarantee crouch consistency by embedding the previous mechanism in the file system. To make sure it is possible to ensure the crouch consistency, there has been support for crouch consistency that covering two fundamental guarantees. The first guarantee is durability. That is, by some way, the write can become persistent in memory on demand. So here is an example where the CPU together with the cache are volatile and the memory is persistent. In order for the updated cache line that's shown in orange to become persistent, there must be a way to write back the data and guarantee its persistence, then the program can move forward. And another fundamental guarantee is ordering. That is, one write can become persistent in memory before another write. So in the same example, we have one cache line being written back to memory, and once it's guaranteed to be persisted, the software can issue another cache line and write it back. To make sure we can make the programming possible, there have been hardware support providing low-level primitives for crouch consistency. So Intel has introduced new instructions to x86. By using a combination of CLW and SFENS, the persistent data can be first written back by the CLW, and the SFENS guarantee the CLW's completion, so that data is guaranteed to be persisted after these two instructions issued. And similarly, ARM has instruction called DCCVAP and followed by DSB fence to serve the similar functionality. And now let's take a look how we can use low-level primitives for programming. So here we have a persistent memory, and we want to store an array on the memory. To update the array, say we want to update the second item from B to E, we want to have the procedure crash consistent. In other words, if the procedure fails due to, say, a power failure or system crash, we need to have the updated data either roll back to the original version of B or roll forward to make it complete. Or by the other ways to guarantee we don't have any middle state that's partially updated. So the question is, how can we update B in such a crash-consistent manner? And let's take a look at the mechanism of undo logging as an example. So before we do the coding, we're going to design a mechanism based on undo logging to guarantee the recovery procedure is possible. So first, we want to have a backup of the copy B before we move forward on the update. So this way we already have a backup for rollback. And once the backup is complete, then we can safely do the in-place update. And finally, we want to commit the update, making sure that this update is already in the memory and we don't have the backup there anymore. And among these three steps, they have to be strictly ordered. And further, everything has to be persistent in the end. So here is a code example according to the design that we discussed previously. Similarly, we can divide the code into three steps: backup, update, and commit. And in the backup step, the program first copies B to the backup location, which is a separate position in the persistent memory, and set valid bit to 1 because we want to make the backup valid so we can use it in recovery. So both backup and valid are marked in gray color because at this moment we haven't flushed the cache yet. So we don't know whether data has been written back to memory or not. We just keep it at gray for kind of an uncertain state. And then we issue a persist barrier. In x86, the persist barrier could be a combination of CLW and sfence. And then, after the backup has been written to memory, we can perform the in-place update in the array. Again, it's E. The E is in gray color because we haven't written back yet. Then we unset the valid bit, making it 0, and finally issue another persist barrier to write back both E and the 0 of valid bit. This example seems correct because we have persist barriers in the middle of the stages to make them happen in a certain order, and we persist everything in the end using persist barriers. But what if there's a failure? Because of the writes can reorder due to the memory hierarchy, there's no guarantee that backup will be written to memory before the valid equals to 1. So in case of reordering, we could have a backup become not persisted, but a valid bit already persisted due to the reordering. So in the recovery procedure, we are looking at the valid bit. Okay, this is 1, and then we take the backup copy and use it to roll back in the array. And in this case, we're just writing potentially garbage data to the array, which is incorrect. So the fix to that is we need to insert more persist barrier to prevent such a reordering to happen. So we have a persist barrier between line 1 and the current line 3 to make sure the backup is set before we can set the valid bit. And similarly, we have another persist barrier between line 5 and line 6 to have the update persisted in place. Then we invalidate the backup. Otherwise, we may not have anything to roll back. If the value is already set to 0, then we will take the data that's already existed in the in-place update. So because reordering has been disallowed, we always have a correct system. So now move on to persistent memory programming support on the library side. So the library provides transactions to make such a low-level programming much simpler. A very typical example is Intel's PMDK, which provides both the low-level sort of wrapper for these hardware primitives and high-level transactions like libpm-obj. And there have been a lot of academia works to make the programming simpler, because using those low-level primitives is very hard. So here I'm showing a code example that's using a PMDK transaction to implement a list append operation, which is given a persistent linked list, we want to append a new node to its head. here I'm using these TXP and TXN to mark out the transaction, but within the transaction, I simplify some of those wrappers, such as DRW, that retrieves a persistent pointer to perform direct access. So first, the program creates a new node because we need to create a node, then we perform the append. And then you use the TXadd to make a backup or a snapshot of the list head. After the snapshot is made, the program moves on to the next line, that's making the new node the new head, basically changing the head to the new node pointer. Because we already had backup, the step is already correct. Then we have a list length plus to increment the length, because we just append a new node, the length has to be greater, right? And in this example, although it seems we have the TXadd for the head, but the program misses a TXadd for the original length. So the length is not backed up before performing the update. The consequence could be the recovery program may need the length for correct, say, traversal of the list. So if the length is already still the old value, some of the items might be missed in the end. And the fix is to add a TXadd before the length plus to make a snapshot for recovery. And now it is correct. So as we can see here, even with the transaction makes the code a lot simpler, we still need to have a very good understanding of the promise from the transaction, and also what we really want to modify. What will be needed in the recovery procedure. So we can conclude that programming is hard for persistent memory. The programmer first needs to have a knowledge about how to design a cross-consistency mechanism, and then implement it correctly. Especially using low-level primitives, they have to have a very good understanding about what the hardware provides and what they really want the program to behave in terms of cross-consistency. To make such a task simpler, our previous work, PM-test, tests two fundamental guarantees of durability and ordering. And PM-test provides two types of assertion-like annotations, which asserts whether the program is in a durable, whether some location is a durable state given a certain point in the program, and what is the ordering of two writes. And it can cover both types of program on the based on the low-level primitives and high-level transactions. And given the first example of array update, we can apply PM-test to see whether the backup is persisted in the end of these two update procedures. And second, we can use assertion on the ordering to check whether backup has been persisted before the valid. Because we didn't issue a fancy in the middle of those two steps, the second checker on whether backup is persisted before valid will fail. And then we can see where the bug is and fix it. But it doesn't solve all the problems. What if there's something going on in the recovery stage? And what happens after that? So now we introduce the idea of interactions across the failure. So given execution that's before failure, we call it pre-failure stage. It happens normal execution such as list append or updating a location in the array. And after failure, the post-failure stage, which is the stage after failure, will perform some recovery by accessing data that's already being logged or being kept in the snapshot, and then perform the resumption of the execution by keep inserting new items to the data structure, for example. And there's an interaction across the two stages, which we call cross-failure interactions. If there's an incorrect interaction across the stage, the recovery may not be correct and fail to meet the cross-consistency guarantee. So there's a need for holistically detect bugs across both stages. If one stage is incorrect, then the whole program cannot recover properly because they are equally important. And given this idea, the goal of this work are the following three. First, we want to categorize incorrect interactions across failure. And then, given this categorization, we want to precisely define each type of incorrect interactions. And finally, we want to implement the tool to detect such incorrect interactions such that we can find cross-consistency bugs and make the program recoverable. And so far, I have talked about a relatively long background on motivation, how programming for persistent memory is hard, and why only testing one stage is insufficient. And next, I'm going to move on to cross-failure bugs, the categorization part. We identified briefly two categories of cross-failure bugs. The first type is a cross-failure race, and the second type is cross-failure semantic bug, which I will talk about in detail later. Now let's take an example of cross-failure race. The example is the same as what I showed you earlier as the first example. The program first makes a backup of the persistent array, and then it sets the value bit of the backup. If there's a failure, then the post-failure program needs to read from the backup, which may not be actually written back, if the value is already set to 1 in the memory. So such a situation makes the program status of the backup unknown. It may be something not fully persisted, so it is not safe to take the value, right? And such uncertainty makes us come idea of making an analogy between the persistent domain and concurrency. In the concurrency domain, we have a writer and we have a reader, both of which are accessing the shared location. Say an integer that the writer is trying to set it to 10, and the reader wants to see the current value of the integer. Because those two are happening at the same time, there's no guarantee what is the value the reader will obtain in the end, which is data race. So back to the persistent domain, because of the similarity, we call pre-failure a writer and post-failure a reader, because the pre-failure is trying to update some location, and the post-failure is trying to read from that location for certain recovery, for example. And because they are so similar, we call it as a cross-failure race, that is reading from a potentially non-persistent location. And more specifically, the definition of cross-failure race is the post-failure execution tries to read from data modified by pre-failure execution, but it is not guaranteed to be persisted before failure. Such a location that is causing a cross-failure race could be something cache evicted and written back, or it may not be evicted, so it remains fully in the cache, or it could be partially evicted if the data structure is very large, say multi-cache lines. So some of those cases will lead to the data to be unusable, like partially evicted. We have part of data being the latest and part of being the stale version. And because of the uncertainty, there could be undefined behavior during the post-failure recovery procedure, or even the post-failure resumption. But now there's a question: do all cross-failure races lead to bugs? Is there any exception that there's a race but there's no bug? So let's still go back to the example, and we fix this buggy example by using a persist barrier. We place it in the middle of the backup stage and setting the valid. So now we still need to read from the valid bit for the recovery, because otherwise we don't know whether the backup has been persisted or not. So it seems like there's a cross-failure race on the valid, right? Because valid is not guaranteed written back by the time the failure happens, but it is being read from the post-failure stage. But we found that the value can either be 1 or 0, because it's just a single bit or like an integer that's telling the status of the backup. So all the outcomes are well defined. Given that the valid is value equals to 0, we know that the array keeps the latest data. And if the value is 1, we know the backup is keeping the latest data. And in both cases, the value is well defined, so we don't have any problem. And we found that actually the correct recovery actually relies on such intentional race. So we call such a behavior benign cross-failure race, because it's not causing any problem. More specifically, the definition of a benign cross-failure race is the post-failure execution intentionally reads from some potentially non-persistent data without causing any inconsistencies. And because it is deterministic, we regard it as correct. Again, we make an analogy with the concurrency domain. We have the writer and the reader again, but the shared location in the middle is some synchronization primitive, say a locking variable. Because of the behavior is well defined under such a locking variable, either one gets a lock or the other gets a lock. So we don't have any problem here. So far we have talked about accessing non-persistent data in post-failure, that leads to undefined behaviors that's causing a cross-failure race, it is a bug unless it is a benign cross-failure race. Then how about we access some inconsistent data that is regarded as inconsistent by the program but may already become something persisted, not leading to a cross-failure race? Then what kind of situation would that happen? So before we talk about the debugging part, let's take a look at the data consistency in persistent memory programs. Persistent memory programming typically follows crouch consistency mechanisms. For example, undo logging that we used in the first example, or redo logging, which is used by internal PMDK, for example. And also there are other things such as checkpointing, shadow paging, etc. And most mechanisms maintain two versions of data. One version is regarded as consistent, and the other version is regarded as inconsistent because it is under update. And versioning is managed by a commit variable, such as a value bit in the undo log-based array update. So, depending on which version the commit variable is pointing to, we will use that version as a consistent copy for recovery. But if the commit variable is pointing to a version that is already known to be inconsistent by the program semantic, then a cross-failure semantic bug occurs. The inconsistent copy could be, say, a stale undo log, where the update is already done, but we still trying to access the log, or some old checkpoint that is not supposed to be used for recovery. We're supposed to use the latest checkpoint by program semantics, for example. And now we have examples that's showing cross-failure semantic bug. We have the version of the first example, but with persistent barriers inserted in the 3 stages to make sure it's correct. But the program makes a mistake that setting the value bit to the wrong value. So in the first part, it's supposed to be setting to 1 because the backup is a valid copy, but it sets to 0. And same thing happens in the invalidation of the backup, which is setting to 1 instead. So first stage, the program still makes a backup and make it persisted, and then performs the update in the location of the array. And in the commit stage, the program tries to invalidate the backup by setting the value bit. After failure, the post-failure needs to check the value bit and apply the backup if the value is already set to 1. In this scenario, value is set to 1, right, but the copy is not the backup copy is stale, so you're not supposed to read such a backup, which is causing a cross-failure semantic bug. So a cross-failure semantic bug, in summary, is read from a semantically inconsistent location. More specifically, a cross-failure semantic bug is the post-failure execution tries to read from data updated during the pre-failure execution that are semantically inconsistent according to the program logic. And cross-failure semantic bug, because it's not a cross-failure race, all the outcomes are incorrect. So it is deterministically incorrect. So in summary, we have to identify 2 types of cross-failure bugs, cross-failure race and cross-failure semantic bugs. And inconsistencies are due to the incorrect interactions of cross-failure. The pre-failure stage, if it doesn't implement a correct mechanism, or the post-failure stage, which doesn't properly restore the status, can lead to the program to be buggy and not recoverable. And here's a Venn diagram showing such categorization. We have the left red circle showing cross-failure race, and we eliminate the part that's a benign cross-failure race, which is the correct behavior. And the other side, we have a cross-failure semantic bug, and both of them can overlap because there could be something that's not guaranteed to be written back and also regarded as not a consistent copy by the program logic. So something can be both a cross-failure race and a cross-failure semantic bug. And now let's move on to the detection of based on XFDetector. The cross-failure detector detects incorrect interactions of cross-failure for cross-consistency bugs. So it could be some incorrect interactions from the recovery procedure to the normal execution in the pre-failure, say reading from a stale copy as the recovery, or it could be the resumption of the program execution. Say the program tries to keep updating linked list, but because it has to access some value that is not guaranteed to be consistent, then it is also triggering a cross-failure bug. So Now I'm comparing the cross-failure detector with previous works, which only testing pre-failure bugs alone. And because we cover in both stages, cross-failure detector has better capability in detection as compared to previous works. Because cross-failure detection relies on the failure that's triggering the pre-failure stage and post-failure stage, we need to inject a failure to the program. So given the code from the first example, the question is, where do we place the failure? One naive solution is to randomly place the failure to whenever the random number tells. But the problem is there could be some code region that is buggy but not captured by the failure, so there's no post-failure execution to trigger the cross-failure bug. Another way is to inject the failure at every single position, but this can be extremely slow. And think about the program can potentially have writes reorder because of the memory hierarchy, then there could be almost infinite number of possibilities where the failure could happen. Then there's no way we can really detect the bug within a reasonable amount of time. So our solution is to smartly inject failure only before each ordering point, such as the persist barrier. The insight behind that is we know data will become potentially consistent after persist barrier. Say we write back some piece of data after the persist barrier, but not the other way around. So we only inject failure into the point that before data can become potentially consistent. And with such an injection, we can cover all cases. Now let's move on to the detection mechanism of cross-failure detector. Cross-failure detector collects trace of both the pre-failure and post-failure stages, and maintain a shadow persist memory to track the persistency state and consistency state. During runtime, it replaces both traces. The pre-failure trace updates the shadow persist memory by updating the persistence and the consistency of the location being updated. The persistency is guaranteed by the instructions, say CLW and SFANS. So we can, by replaying those instructions, we can update the state. And the consistency state is defined by the program semantics. So when testing those low-level programs based on the low-level primitives from the hardware, the program has to provide some annotation for locations such as the commit variables. And for details about annotation, please take a look at our paper. And in the post-failure stage, the program checks those corresponding state of the address, see whether it is a persistent location or it is a consistent location. And now let's summarize the detection with a workflow. First, the program needs to provide annotation. For those transaction workloads, we don't have to annotate the commit variable, but instead only provide a region of interest surrounding the part that we want to test. And then, cross-failure detector automatically injects failure to the points that we consider are important, basically right before the ordering points, like a persist barrier. And then at runtime, the cross-failure detector performs tracing, having the pre-failure trace and post-failure trace for both of the failure points in the example. And then it detects the bug by replaying the trace and see whether there's any incorrect cross-failure interactions. And the first two stages are performed offline, and the last two stages are performed at runtime. And now let's take a look at the evaluation of performance and capability of detection. The methodology of the evaluation is as follows. We have a platform using Intel's latest Cascade Lake and DC persistent memory. We use Intel's Pin tool to trace the pre-failure and post-failure traces for detection. And the test program includes the micro benchmarks from Intel's PMDK library, and also two real-world databases, Redis and Memcached, which are also based on PMDK. I'm now showing the original lines of code in these workloads, and then the annotation on the right-hand side. As you can see, the annotation is a very small fraction as compared to the original code, meaning that it is very efficient in terms of detection. Programs don't need to do a lot of work, and they don't have to really understand the program semantics, given that the program is already based on a transaction. But for these low-level based workloads, they still need to have an idea of what is a commit variable. Now I'm showing the detection performance of cross-failure detector of testing one transaction. The y-axis is showing the execution time in seconds. Each of the bar is divided into two parts, the post-failure part and the pre-failure part. As you can see, pre-failure is taking only a small fraction of time, but the post-failure is taking the majority of time. The reason for that is because the pre-failure execution only needs to happen once. But for every single failure point within the pre-failure stage, the post-failure needs to be triggered. So the accumulated post-failure execution time is taking the majority. And we are now normalizing the execution time of XFDetector over the pure pin tool. As you can see, it's not taking a lot of time, considering that the post-failure needs to be happened repeatedly. So we can conclude that cross-failure detector is very efficient at detection. So given a faster tracking method in the future, we can make the detection performance a lot better. And then let's take a look at the performance of testing multiple transactions. The y-axis is showing the execution time still in seconds, and the x-axis is showing the transaction number. As you can see, the execution time grows linearly with the number of transactions. The reason for that is because the program does not need to do extra work given that there are more transactions in most of the cases. Because, say, the program typically employs a very efficient mechanism, say, only roll back the last incomplete transaction instead of all the previous transactions. And finally, we evaluate the detection capability. We validate with synthetic bugs into those macro benchmarks. And here I'm showing the number of test cases we used. And we also find new bugs that has not been identified by previous work, mostly due to the lack of cross-failure feature. We have 2 new bugs in HashMap Atomic, and 1 bug in Redis, and another bug in the PM-optimized library. And this is the first example that I'm showcasing now. It's a bug in HashMap Atomic. In the creation function, the program tries to initialize metadata, such as hash functions. But because those updates to the hash functions are not wrapped up in a transaction, if there's a failure, the recovery program might be reading from some garbage data of the hash function. So the later execution may be relying on those hash functions and cause the program to be buggy. So a failure during initialization can cause resumption to fail when accessing inconsistent metadata in this example. The second bug I'm showing now is Redis. There's a init persistent memory function that performs a initialization of persistent memory if the memory pool has not been set up yet. In the last step of the setting of new pool, the program writes to a number of dictionary entries in the hash in the Redis. Because initialization is not covered by any cross-consistent mechanism, the number of dictionary entries can be a garbage value, could be any value. So the recovery program may be checking a value that's greater than 0, and tries to recover it. But because the program is just initialized, there's no entry for it to recover from, and this is causing a bug. So in summary, a persistent memory program has 2 equally important execution stages that are the pre-failure stage and post-failure stage. This work defines the 2 categories of bugs across the failure: cross-failure race, unless it is benign, and cross-failure semantic bug. And we provide cross-failure detectors that holistically test both stages. XFDetector detects 4 new bugs in existing persistent memory programs, and XFDetector is open sourced at the following link. And thank you for listening to my talk, and welcome to look at my paper and check out my artifact.